I've been thinking a lot about nothing lately, which is, I know, a strange thing to say, right? Because how do you think about nothing? What is there to think about? But that's exactly the thing, you see, that's exactly where this gets interesting, because nothing, it turns out, might not actually exist. Not in the way we think it does. Not really. And the more physicists have looked at this question, the more they've realized that nothingness, true nothingness, complete and utter absence of everything, might actually be impossible. Not just hard to achieve, not just difficult to create in a laboratory, but fundamentally, deeply, perhaps necessarily impossible. And that's one of the most profound things about our universe. When you think about nothing, what comes to mind? Probably empty space, right? The void between stars, maybe, or the emptiness of a vacuum. You imagine clearing everything away, removing all the matter, all the energy, all the light and particles and fields, until there's just, nothing left. A blank slate, pure emptiness. It seems so simple, so straightforward. After all, nothing is the absence of something, isn't it? It's what you get when you take everything away. It's the default state, the starting point, the zero on the cosmic number line. But here's the thing, and this is where our intuitions start to fail us. Nothing isn't simple at all. In fact, nothing might be the most complicated, most unstable, most impossible thing we could imagine. You see, for most of human history, nothing seemed pretty straightforward. The ancient Greeks, some of them anyway, believed in the void, the empty space between atoms where truly nothing existed. Aristotle, on the other hand, he rejected the whole idea. He thought nature abhorred a vacuum, that empty space couldn't really exist because if it did, things would move infinitely fast through it, which seemed absurd. And for a long time, people kind of went back and forth on this. Some believed in the void, others didn't. But they were all talking about the same basic concept, a place where there's no stuff, no matter, no things, just emptiness. And then we started doing experiments. In the 1600s, people like Torricelli and von Guericke figured out how to create vacuums, or at least pretty good approximations of vacuums. They pumped the air out of containers and showed that yes, you could have spaces with nothing, or almost nothing, in them. And that seemed to settle it, right? Nothing was real. You could make it, you could study it. It was just empty space, the absence of matter. Simple. But then we discovered that light was a wave. And that presented a problem because waves need something to wave in. Water waves move through water, sound waves move through air. So light waves, they must move through something, right? And so physicists invented this substance, this stuff they called the luminiferous ether, which filled all of space and allowed light to propagate. So suddenly, nothing wasn't nothing anymore. Even empty space was full of this ether, this invisible medium. Of course, that turned out to be wrong. Einstein showed that light doesn't need a medium, but the point is we were already starting to realize that empty space might not be so empty after all. And that's where things really started to get strange, because in the early 20th century, we discovered quantum mechanics. And quantum mechanics, it changed everything. It changed how we think about matter, how we think about energy, how we think about reality itself. But maybe most importantly, it changed how we think about nothing. Because in quantum mechanics, nothing isn't stable. It can't be. The very laws that govern the universe at its most fundamental level seem to forbid true nothingness. Let me try to explain why, and I should warn you, this is where things get a bit counterintuitive, a bit strange. But stay with me because this is important, this is profound. At the heart of quantum mechanics is something called the Heisenberg uncertainty principle. You've probably heard of it, right? It says that there are certain pairs of properties like position and momentum or energy and time that you can't know simultaneously with perfect precision. The more precisely you know one, the less precisely you can know the other. It's not a limitation of our measuring instruments. It's not that we just need better technology. It's a fundamental feature of reality. The universe itself doesn't have definite values for these properties at the same time. Now, you might be thinking, okay, that's interesting, but what does that have to do with nothing? Well, everything, actually. You see, one of those uncertainty relationships is between energy and time. The more precisely you know when something happens, the less precisely you can know its energy, and vice versa. And here's the crucial bit. This applies to empty space too. If you have a region of space and you try to say that it has exactly zero energy, that there's absolutely nothing there, you're specifying its energy with perfect precision. You're saying Definitively, the energy here is zero. No fluctuation, no variation, just zero. But quantum mechanics says you can't do that. If you specify the energy that precisely, then the time becomes completely uncertain, which leads to all sorts of contradictions and impossibilities. So instead, what happens is that even empty space, even the vacuum, even nothing, must have some uncertainty in its energy. It can't just sit there at exactly zero energy. It has to fluctuate, it has to vary, it has to have some something in it. And this is where it gets really wild, because these aren't just abstract mathematical fluctuations. These energy fluctuations are real, they're physical, they have consequences. What happens is that pairs of particles pop into existence out of nothing, exist for the briefest instant, and then annihilate each other and disappear back into nothing. Virtual particles, they're called. A virtual electron and its antimatter partner, a positron, can just appear out of empty space, live for a tiny fraction of a second, and then destroy each other. And this is happening everywhere, all the time, throughout all of space. The vacuum, the nothing, is actually seething, boiling with these virtual particles constantly appearing and disappearing. Now, I know what you're thinking. You're thinking, wait, if they appear and then disappear so quickly, are they really there? Do they actually exist? And that's a good question. That's exactly the right question to ask. And the answer is, well, yes, they do exist. We know they exist because we can see their effects. These virtual particles, even though they're fleeting, even though they're temporary, they have real measurable consequences. They affect how real particles behave. They change the energy levels of atoms. They even create forces that we can detect in laboratories. There's this famous experiment, the Casimir effect, that demonstrates this beautifully. If you take two metal plates and put them very close together in a vacuum, they feel an attractive force pushing them together. Now, why would that be? There's nothing between them, right? Just empty space. But actually, no, there's not nothing. There's all these virtual particles popping in and out of existence. And here's the thing. Between the plates, only virtual particles with certain wavelengths can exist because the plates are so close together. Outside the plates, all wavelengths are possible. So there's more quantum activity, more virtual particles outside the plates than between them. And this creates a pressure, an imbalance that pushes the plates together. We can measure this force. We can see it in experiments. The nothing between those plates has real physical effects. And this isn't just some quirky little effect that only matters in carefully controlled laboratory experiments. This is fundamental to how the universe works. These quantum fluctuations, this impossibility of true nothingness, they're built into the fabric of reality. They affect every atom, every particle, every field. In fact, and this is remarkable when you think about it, these fluctuations are part of why atoms are stable at all, why they have the energy levels they do, why chemistry works the way it does. The fact that nothing can't be nothing is literally essential to our existence. But let's dig deeper into this, because there's more to it. There's always more. When physicists talk about the vacuum, they don't just mean empty space in the way we usually think about it. In modern physics, particularly in quantum field theory, the vacuum is something much more sophisticated, much more strange. It's not just the absence of particles, it's actually a state of quantum fields. And this is important, this is crucial to understanding why nothing might be impossible. You see, in quantum field theory, everything, every particle, every bit of matter and energy is understood as an excitation of a field. Electrons are excitations of the electron field. Photons are excitations of the electromagnetic field. Quarks are excitations of the quark field, and so on. These fields exist everywhere, throughout all of space, and particles are just sort of ripples or vibrations or disturbances in these fields. It's like the field is an ocean, and particles are waves on that ocean. Now, when we talk about the vacuum, what we mean is the lowest energy state of these fields. It's the ground state, the state where there are no particles, no excitations, no ripples on the ocean. And you'd think, okay, so the vacuum is when the fields are just flat, calm, zero, right? But no, that's not quite right either, because even in this lowest energy state, the fields aren't really at zero. They can't be at zero because of those quantum fluctuations we talked about. The uncertainty principle applies to fields just as much as it applies to particles. So even in the vacuum, even in the lowest energy state, the fields are still fluctuating, still varying, still never quite zero. And these field fluctuations, they have energy. They must have energy because energy is conserved. and these fluctuations are real, physical things. This is called zero-point energy, the energy that remains even when everything is in its lowest possible state, even when you've removed all the particles and all the heat and everything else you can remove. You might think that the lowest energy state would have zero energy, and that seems logical, that seems like what the name should mean, but it doesn't. The lowest energy state still has energy, and it's not a small amount either. When you add up all the zero-point energy from all the quantum fields throughout all of space, you get an absurdly large number. Embarrassingly large, actually. So large that if it were all real, if it all contributed to the energy density of the universe, space itself would curve so dramatically that the universe as we know it couldn't exist. Now, this presents a problem, obviously. We call it the cosmological constant problem or the vacuum catastrophe, and it's one of the deepest unsolved problems in theoretical physics. The quantum field theory calculations suggest that empty space should have a huge energy density, but observations suggest it has a very, very small energy density, or possibly even zero. Why is there such a huge discrepancy? Why doesn't all that zero-point energy have the gravitational effects we'd expect? Nobody knows, not really. There are various ideas, various proposals, but no consensus, no clear answer. It's one of those mysteries that keeps physicists up at night. But here's what's interesting for our purposes, for this question of whether nothing can exist. Even if we don't understand why the vacuum energy is so much smaller than we calculate, even if we can't explain the cosmological constant problem, the fact remains that the vacuum, the nothing, has energy. It has structure, it has properties. It's not just blank emptiness, it's something, not nothing. And that something has consequences, real physical consequences that affect how the universe behaves. Let me give you another example of this, another way that nothing turns out to be something. In the standard model of particle physics, which is our best theory of how particles and forces work, there's something called spontaneous symmetry breaking. And what this means basically is that the vacuum, the lowest energy state, isn't symmetric in the way you might expect. The laws of physics might be symmetric, but the vacuum state itself isn't. It's like a ball sitting at the top of a hill that's perfectly symmetric, perfectly circular. The ball could roll down in any direction. All directions are equivalent, but once it does roll down, once it settles into a valley, that particular direction is special. The symmetry is broken. The most famous example of this is the Higgs field. The Higgs field fills all of space, and its vacuum state, its lowest energy configuration, isn't zero. It's a non-zero value, and this non-zero vacuum value is what gives particles their mass. The Higgs field is sort of always on, always there, everywhere, even in empty space. Particles moving through empty space are actually moving through this Higgs field, and their interaction with the field is what makes them heavy, what gives them inertia. So even if you could somehow remove all particles from a region of space, you'd still have the Higgs field there, sitting in its non-zero vacuum state, waiting to give mass to any particle that happens to pass through. And this is true for other fields too, not just the Higgs. The vacuum states of various quantum fields have structure, have properties, have effects. Empty space isn't a blank slate. It's more like a canvas that already has a painting on it, a painting that influences everything that happens on top of it. The nothing we're moving through right now as you read this, it's not empty. It's full of fields in their ground states, full of zero-point energy, full of virtual particles flickering in and out of existence. You're not in nothing, you're in something, even when you're in what seems like empty space. And here's where this gets really, really deep, because if nothing is impossible, if even empty space is something, then what does that mean for the question of why there is something rather than nothing? This is one of the oldest philosophical questions, right? Why does anything exist at all? Why isn't there just nothing, pure nothing, absolute nothing? Many people have suggested that nothing is the natural state, the default, and that something, existence, the universe, requires an explanation. But maybe that's backwards. Maybe nothing isn't the natural state. Maybe nothing isn't even possible. Maybe something, some kind of something is actually necessary, is actually inevitable. Think about it this way. If the laws of quantum mechanics are correct, and all the evidence suggests they are, then nothing is unstable. A state of true nothingness, with no fields, no particles, no energy, no anything, would violate the uncertainty principle. It would be a state with precisely zero energy, which is forbidden. So if you somehow started with nothing, with absolute true nothing, quantum mechanics says it couldn't stay that way. it would have to fluctuate. It would have to generate something. Virtual particles would appear, fields would activate, energy would manifest, nothing would become something, and it would do so necessarily inevitably because the laws of physics demand it. Now, I should be careful here because this isn't quite the same as explaining why there are laws of physics in the first place, why there's a universe with quantum mechanics and fields and particles rather than no universe at all. That's a deeper question, maybe the deepest question, and I'm not going to pretend I have an answer to it. But what I'm saying is that given the laws of physics we observe, nothing is unstable, nothing can't persist, nothing must become something. And that's profound, isn't it? That's a very different way of thinking about existence. Some physicists have taken this idea even further and suggested that the universe itself might have originated from nothing, from a quantum fluctuation in nothing. This is the idea behind certain quantum cosmology models, where the universe is essentially a virtual particle that popped into existence out of the vacuum and then, unlike most virtual particles, didn't immediately disappear, but instead inflated and expanded and became the vast cosmos we see today. It's a strange idea, I'll grant you, and there are many questions about it, many problems to work out, but the fact that physicists take it seriously, the fact that it's even a possibility we can discuss scientifically, tells you something about how deeply we've had to revise our notion of nothing. And there's another angle to this too, another reason why nothing might be impossible, and it has to do with information. In recent years, physicists have started thinking about the universe not just in terms of matter and energy, but in terms of information. Information, in the technical sense that physicists and computer scientists use the term, is a fundamental thing. It's not just something abstract, something conceptual, it's something real, something physical, something that can be quantified and measured. And here's an interesting thing about information: it seems to be conserved. Not in the same way that energy is conserved exactly, but conserved nonetheless. Information can't be created or destroyed, it can only be moved around, transformed, scrambled. This is related to the famous black hole information paradox, which I won't go into in detail, but the basic idea is that if information is truly conserved, as quantum mechanics suggests it must be, then nothing can ever truly vanish. Even if you destroy something, even if you annihilate it completely, the information about what it was, how it was configured, all of that has to go somewhere. It can't just disappear into nothingness. And if information can't be destroyed, if it can't become nothing, then in some sense, nothing is impossible on an informational level too. Every bit of information that exists, every configuration, every state, every quantum possibility, it has to remain in existence in some form, somewhere, somehow. Maybe as correlations between particles, maybe as subtle patterns in quantum fields, maybe as something we haven't even thought of yet, but it can't just vanish. The universe might be able to transform information, might be able to hide it or scramble it beyond recognition, but it can't make it nothing. Let me tell you about another aspect of this, something that comes from cosmology, from studying the universe at its largest scales. When we look out into space, when we observe the universe, one of the most remarkable things we see is that it's not in thermal equilibrium. It's not at maximum entropy, not in its most probable state. There are stars and galaxies and structures, there are temperature differences, there's free energy available to do work. And this is strange, right? Because the second law of thermodynamics says that entropy always increases, that systems tend toward equilibrium, toward maximum entropy, toward a kind of sameness, a kind of thermal nothingness where nothing interesting can happen anymore. But the universe isn't there yet. It's far from equilibrium, and it has been since the beginning. And this raises a question: why? Why did the universe start in a low entropy state? Why wasn't it born already at maximum entropy, already in equilibrium, already in a state of sort of thermodynamic nothing? And the answer seems to be that a state of nothing, a state of maximum entropy, a state where nothing interesting can happen, is actually not the lowest energy state. It's not stable. The universe with structure, with stars and galaxies, with fields and particles and energy differences, that's actually a lower energy state, a more stable configuration than a featureless void would be. This connects back to what we were saying earlier about the vacuum having structure, having energy, A completely uniform, featureless universe wouldn't be nothing. It would be something very specific, a very particular state of the quantum fields, and that state isn't stable, isn't the ground state. The ground state, the lowest energy configuration, involves symmetry breaking, involves the Higgs field having a non-zero value, involves quantum fluctuations, involves all these things that make the universe interesting and structured rather than blank and empty. And you can think about this in terms of information too. A state of maximum entropy, a state of perfect thermal equilibrium, is actually a state of maximum information in a certain sense, because every microstate is equally probable, and you need the maximum amount of information to specify which particular microstate the system is in. Whereas a low entropy state, a structured state, is one where there's order, where there's pattern, where you need less information to describe it because it's not just random. So nothingness, in the sense of maximum entropy, actually requires more information than somethingness. The universe being structured and interesting is actually simpler in an informational sense than it being in a featureless high entropy state. But let's think about this from a different angle now, from a more philosophical perspective. What do we even mean when we say nothing? What are we referring to? When I say imagine nothing, what comes to your mind? Probably something like empty space, like I said before, or maybe just blackness, darkness, and absence of light. But is that really nothing? Space itself is something, isn't it? It has dimensions, it has properties, it has a geometry. Even if there's no matter in space, no particles, no light, space itself is still there. So that's not nothing, that's something. Okay, so maybe nothing means no space either. No space, no time, no dimensions, no anything. Just, well, nothing, pure absence. But here's the problem, we can't really imagine that. We can't really conceive of it. Because our minds, our thoughts, our imagination, they all exist in time. They all unfold as processes. They all require some kind of framework to operate in. When you try to imagine no space and no time, what you're actually imagining is probably something like empty space or blank darkness, which isn't really no space. It's just space with nothing in it, true nothingness. Absolute nothingness might be literally unimaginable, literally inconceivable, because conceiving of something requires a conception, requires a mental model, requires some kind of structure, and nothing, by definition, has no structure. So maybe the question, why is there something rather than nothing, is a bit like asking, why is there up rather than down? Or why is there before rather than after? These aren't really questions with answers because the concepts themselves are relative. They're defined in relation to each other. Something and nothing might be like that too. Nothing doesn't exist on its own as an independent concept. It's just the negation of something, the absence of whatever we're considering. And if that's the case, then nothing isn't really a possible state of affairs. It's just a linguistic construct, a way of talking about absence. But wait, because there's another way to think about this. Another philosophical tradition that's relevant here. Some philosophers, particularly in the Buddhist tradition, have argued that nothingness or emptiness or the void isn't really nothing at all. It's not absence, it's more like potentiality, possibility, the ground from which things arise. In this view, emptiness isn't the opposite of existence, it's the basis of existence. It's not that there's nothing and then something appears. It's that emptiness and form, void and matter, nothing and something. They're all interconnected. They're all aspects of the same reality. And you know what? That actually resonates with what modern physics tells us. The quantum vacuum, with its zero-point energy and its virtual particles and its field fluctuations, it's kind of like that. It's not absence, it's potentiality. It's a state from which particles can emerge, from which energy can manifest, from which something can arise. The vacuum is pregnant with possibility, seething with potential, and in that sense, it's not nothing at all, even if there are no particles, no energy in the conventional sense. Let me try to connect this to something more concrete, something closer to everyday experience. You know how sometimes people talk about silence as the absence of sound? We think of silence as nothing, as quiet, as peace. But if you've ever been in a truly quiet environment like an anechoic chamber, one of those rooms where all sound is absorbed and there's no echo, no reverberation, no ambient noise at all, you realize that silence isn't really nothing. It's oppressive, it's overwhelming, it's something. You can hear your own heartbeat, your own breathing, the blood flowing through your ears. You can hear sounds that you never knew existed because they're always masked by environmental noise. Silence, true silence, isn't the absence of sound, it's the presence of sounds you usually don't notice. And I think nothing is like that too. True nothing, if it could exist, wouldn't be the peaceful absence we imagine. It would be something strange, something unstable, something that immediately fills itself with something else. Or maybe it can't exist at all, and what we call nothing is always already something, just something so subtle, so fundamental, so omnipresent that we don't usually notice it. There's also this interesting thing that happens when you start thinking about nothing in terms of mathematics and logic. In mathematics, we have the concept of zero, which represents nothing, right? No quantity, no amount, nothing. But zero isn't really nothing, it's a number. It's a specific, definite value that has properties and relationships with other numbers. 0 times anything is 0, 0 plus anything is that thing, and so on. Zero is something very particular, very specific. It's just something that represents an absence of quantity. And then there's the empty set in set theory, the set that contains no elements. That's the mathematical version of nothing, right? A collection of nothing, a set with no members. But even the empty set is a thing, an object, an entity in the mathematical universe. It has properties, it has relationships with other sets, you can perform operations on it. The empty set isn't nothing, it's a very specific something. And this points to a deep issue, a deep problem with the concept of nothing. Nothing is supposed to be the absence of everything, but as soon as you talk about it, as soon as you think about it, as soon as you define it, it becomes something. It becomes an object of thought, a concept, an idea. And ideas are something, not nothing. So maybe nothing is self-contradictory. Maybe it's logically impossible, not just physically impossible. Maybe the very act of conceiving of nothing makes it not nothing. Now, some philosophers have argued that this is just a trick of language, that we're confusing the concept of nothing with nothing itself. The concept of nothing is something, sure, but nothing itself, the actual state of absolute nothingness that would still be nothing even if we can't properly think about it or talk about it. And maybe that's right, maybe there's a real distinction there, but I'm not so sure, because if we can't think about it, can't talk about it, can't in any way access it or know about it, then in what sense does it exist? In what sense is it even a possibility? This is getting pretty abstract, I know, but I think it's important because it shows that the question of whether nothing is possible isn't just a scientific question, it's also a philosophical question, a conceptual question, maybe even a linguistic question. And the answers from these different domains, they kind of converge. Physics says nothing is unstable, philosophy says nothing is inconceivable, logic says nothing is self-contradictory. From every angle we approach it, nothing seems to slip away, seems to become something, seems to reveal itself as impossible. Let's go back to physics for a moment, because there's more to say here about the specific mechanisms that prevent nothing from existing. We talked about the uncertainty principle and virtual particles, but there's another aspect of quantum mechanics that's relevant. The phenomenon of quantum tunneling. Quantum tunneling is when a particle passes through a barrier that, classically, it shouldn't be able to pass through. It's like rolling a ball toward a hill, and the ball doesn't have enough energy to get over the hill, but then suddenly, randomly, the ball appears on the other side of the hill anyway. That's quantum tunneling, and it happens because particles aren't really particles, they're waves, and waves can leak through barriers. Now, what does this have to do with nothing? Well, imagine you somehow had a state of nothing, a region with absolutely no particles, no energy, nothing. The barriers that keep particles out of this region, whatever they might be, they wouldn't be perfect. They couldn't be perfect because of quantum tunneling. Particles from outside the nothing region could tunnel in, could appear inside the nothing, turning it into something. The nothing couldn't maintain itself, couldn't stay nothing, because the quantum world is inherently fuzzy, inherently probabilistic, and tunneling would inevitably occur. And this applies at the cosmological scale too. Some theories suggest that entire universes can tunnel into existence out of nothing, that the quantum vacuum can fluctuate so dramatically that a new universe, a new space-time bubbles off and starts existing. This is related to the idea of eternal inflation, where the universe is constantly creating new pocket universes, new domains of space-time, through quantum processes. And if that's the case, if universes can spontaneously appear from nothing through quantum tunneling, then nothing really can't exist, at least not for long. It would keep producing some things, keep generating universes, keep filling itself with existence. There's also something called the no-hiding theorem in quantum mechanics, which is related to what we were saying earlier about information conservation. The no-hiding theorem says that quantum information can't be hidden in correlations or in inaccessible regions of space or anywhere else in a way that makes it truly disappear. If information seems to vanish from one place, it must have gone somewhere else, must have leaked into the environment or become entangled with other systems or something. It can't just become nothing, can't just cease to exist. And if information can't become nothing, and if everything in the universe has information associated with it, which it does, then nothing, in the sense of a complete absence of information, is impossible. Let me tell you about one more physical phenomenon that relates to this: Hawking radiation. Stephen Hawking discovered that black holes aren't completely black. They actually emit radiation. They actually lose energy over time and eventually evaporate. And where does this radiation come from? It comes from the quantum vacuum at the edge of the black hole, the event horizon. Virtual particle pairs appear at the horizon, and sometimes one particle falls into the black hole while the other escapes as real radiation. The black hole's intense gravity turns virtual particles, which are usually just fleeting quantum fluctuations, into real particles with real energy. And the fascinating thing about this is that it shows again that the vacuum isn't nothing. The vacuum at the edge of a black hole is producing real, observable particles, real energy that we can detect. The nothing of empty space is being converted into something, into radiation, into light, into particles. Black holes are machines that make something out of nothing, or more accurately, they're systems that reveal that nothing was always already something. And as black holes evaporate, as they lose mass and energy through Hawking radiation, they eventually disappear completely. But the information that fell into the black hole, where does it go? This is the black hole information paradox I mentioned earlier. If information can't be destroyed, but the black hole completely evaporates, then the information must be in the Hawking radiation somehow. But how? The radiation seems to be thermal, seems to be random, seems to have no information about what fell into the black hole. This paradox has driven a lot of research in theoretical physics, and the current thinking is that the information is indeed in the radiation, but in a very subtle, very scrambled way, perhaps encoded in correlations between particles that are separated by vast distances. But the point for our purposes is this: even when a black hole disappears, even when one of the most extreme objects in the universe ceases to exist, nothing truly becomes nothing. The information persists, the particles persist, the energy persists. It all transforms, it all changes form, but it doesn't become nothing. Nothing is impossible even in this most dramatic case of something vanishing. Now, I want to think about this from yet another angle, from the perspective of space-time itself. We usually think of space and time as a kind of background, a stage on which events happen, a container in which matter and energy exist. But general relativity, Einstein's theory of gravity, tells us that space-time isn't a passive background, it's a dynamic entity. Mass and energy curve space-time, and curved space-time tells matter how to move. Space-time is something, it's physical, it's real, and it can be warped and stretched and compressed. And if space-time is something, then even if you removed all matter, all energy, all particles, all radiation from the universe, you'd still have space-time itself. You'd still have the geometry, the metric, the curvature, and that's not nothing, that's something very specific, something with properties and structure. Empty space-time isn't the same as no space-time, and no space-time would be what? Would it be nothing? Maybe, but then again, maybe not, because no space-time would also mean no time, and if there's no time, can anything, including nothing, be said to exist? This is where we start hitting the limits of language and conception again, because existence, as we understand it, as we experience it, is fundamentally tied to time. Things exist in time, they persist over time, they change through time. If there's no time, what does it mean for something to exist? What does it mean for nothing to exist? the question almost becomes meaningless. Some theories in quantum gravity, like loop quantum gravity or string theory, suggest that space-time itself might be emergent, might be built up from something more fundamental, something that isn't space or time in the usual sense, maybe discrete loops of gravity, maybe strings vibrating in higher dimensions, maybe something we haven't imagined yet. And if space-time is emergent, if it's constructed from something more basic, then what is that basic level? Is it nothing? Or is it yet another kind of something, just a something so fundamental, so different from our everyday experience that we don't have good words for it? My suspicion, and this is just speculation, is that it's another kind of something. All the way down at every level, there's structure, there's information, there's something rather than nothing. Turtles all the way down, except instead of turtles, it's different kinds of existence, different kinds of being, different kinds of somethingness. Maybe there's no bottom level, maybe there's always another layer beneath, always more structure, always more complexity. Or maybe there is a bottom level, but it's not nothing, it's just the most fundamental kind of something, the you're something, from which everything else emerges. Let's think about this in terms of causation and explanation too. We often think that nothing needs no explanation, that absence is the default and only presence requires a cause. But maybe that's backwards. Maybe something is the default, maybe existence is the ground state, and nothing, if it were possible, would require an explanation. Why would there be nothing rather than something? What would cause nothing? What would maintain nothing? If the laws of physics dictate that nothing is unstable, then nothing would require constant work, constant effort, constant suppression of quantum fluctuations and field excitations and all the things that want to exist. Something is easy, something is natural, something is what happens when you don't do anything. Nothing would be hard, nothing would be unnatural, nothing would require constant intervention. This is a complete inversion of the usual way of thinking about existence, and I find it fascinating. We're so used to thinking that existence is a mystery, that something is what needs explaining, that we've never seriously considered that maybe nothing is the real impossibility, the real paradox, the real mystery. What if existence is just what happens? What if something is the inevitable state, the necessary condition, the only possibility? What if we've been asking the wrong question all along? And you know, this connects to some very old theological and philosophical debates. The medieval philosopher Anselm argued that God necessarily exists because God is defined as the greatest conceivable being, and existence is greater than non-existence, so God must exist. This is the ontological argument, and it's controversial. Most philosophers don't accept it, but there's something interesting in the structure of the argument, in the idea that existence might be somehow necessary, somehow built into certain concepts or certain states of affairs. Now, I'm not arguing that God necessarily exists or that the ontological argument is sound, but I am suggesting that maybe existence itself is necessary. Maybe somethingness is built into the nature of reality in a way that makes nothing impossible. Not because of a divine being or a supernatural cause, but because of the fundamental laws of physics, the nature of quantum mechanics, the structure of information, the instability of vacuum states. Maybe reality just can't be nothing. Maybe being is the only option. Maybe existence is inevitable. And if that's true, if nothing is impossible, then the question, why is there something rather than nothing, isn't really a question at all. There's something because there has to be, because nothing isn't an option, because existence is what happens when you don't actively prevent it. And maybe we don't need to prevent it, maybe we can't prevent it, maybe the universe doesn't give us a choice, something just is, and that's all there is to it. But wait, I can hear you objecting. What about before the Big Bang? What about before the universe existed? Wasn't there nothing then? And that's a good question, but it's based on a misunderstanding. The Big Bang isn't really the beginning of everything. It's the beginning of our universe as we know it, the beginning of the expansion, the beginning of the current configuration of space-time and matter and energy. But what came before? We don't know. Maybe nothing, maybe something. Maybe the question doesn't even make sense because before is a temporal concept and time itself began at the Big Bang. Some cosmologists think there was a quantum vacuum before the Big Bang, a state of nothing that fluctuated and gave rise to our universe. But as we've discussed, that quantum vacuum isn't nothing, it's something. It's a state with properties and structure and energy. Other cosmologists think the universe is eternal, that there was no beginning, that time extends infinitely into the past. And if that's the case, then there never was a time when nothing existed, because time always existed and space-time always existed and something always existed. There's also the possibility of a multiverse, the idea that our universe is just one of many, maybe infinitely many universes. And if there's a multiverse, then even if our particular universe had a beginning, the multiverse as a whole might be eternal, might be infinite, might be a vast something that always existed and always will exist. Nothing would be impossible, not just in our universe, but in all possible universes, in the entire multiverse, in everything that exists or could exist. And this brings us to a deep question about the nature of possibility itself. When we say nothing is impossible, what do we mean by impossible? Do we mean it's physically impossible, forbidden by the laws of physics? Do we mean it's logically impossible, self-contradictory? Do we mean it's conceptually impossible, unimaginable? These are different kinds of impossibility, and they have different implications. If nothing is physically impossible, that means given the laws of physics we have, given the universe we live in, nothing cannot exist. But maybe there could be different laws of physics, different universes where nothing is possible. If nothing is logically impossible, that's stronger. That means in any possible universe, under any possible laws, nothing cannot exist. It's ruled out by logic itself, by the structure of reasoning, by the nature of concepts. And if nothing is conceptually impossible, that means we can't even coherently think about it, can't even imagine what it would be like. I think the evidence suggests that nothing is at least physically impossible in our universe. The quantum vacuum won't allow it. The uncertainty principle forbids it. The Casimir effect demonstrates it. Virtual particles prevent it. But is it logically impossible? Is it conceptually impossible? That's harder to say. I lean toward yes, toward thinking that nothing is impossible in an even deeper sense than just physically impossible, but I can't prove it. It's more of an intuition, more of a philosophical conviction, based on the arguments we've explored about the self-contradictory nature of nothing and the impossibility of truly conceiving of absolute absence. Let me tie this back to human experience, to what this means for us, for our lives, for our understanding of ourselves. If nothing is impossible, if existence is inevitable, if something is all there is and all there can be, then we're not cosmic accidents, we're not unlikely flukes, we're not improbable beings in a universe that could just as easily have been nothing. We're necessary, in a sense, not individually necessary, not you or me specifically, but something like us, some kind of being, some kind of consciousness, some kind of existence. That's inevitable. The universe had to produce something, and that something evolved and complexified and eventually became us. And there's something beautiful about that, something profound. We're not fighting against nothing. We're not temporary islands of order in a sea of nothingness that will eventually reclaim us. We're part of something, part of a universe that's fundamentally, necessarily, inevitably full of being, full of existence, full of structure and complexity and information. Nothing is coming for us because nothing doesn't exist. What exists is transformation, change, evolution, but always in the context of something, always within the framework of existence. Death, from this perspective, isn't becoming nothing, it's becoming something else. The atoms that make up your body don't vanish when you die, they transform, they become part of other things, other beings, other structures. The information that constitutes you, the patterns, the memories, the relationships, they don't disappear entirely either. They persist in the minds of others, in the records you leave, in the effects you had on the world. Nothing is lost to nothing, everything is transformed into something else. And consciousness, that most mysterious of phenomena, the subjective experience of being, of awareness, of feeling, maybe that's not as miraculous as we thought. Not because it's not amazing, it absolutely is, but because in a universe where nothing is impossible, where something is inevitable, where existence is the ground state, consciousness might be a natural consequence, a predictable emergent property of complex systems. If nothing is impossible, then something must be, and if something must be, then complexity must be. And if complexity must be, then maybe consciousness must be too, at least somewhere, at some time, in some form. This doesn't answer all our questions, of course. It doesn't tell us how consciousness works, what it is, why it feels the way it does. But it does suggest that consciousness isn't an anomaly, isn't a violation of the natural order, isn't something that needs to be explained away or reduced or eliminated. It's part of the somethingness of the universe, part of the inevitable complexity that emerges when nothing is impossible, and meaning, purpose, value, those human concerns that we worry about, that we struggle with, they don't require nothing to define them. We sometimes think that life is meaningful because it's finite, because it will end, because it's temporary against a background of nothing. But maybe that's not right. Maybe life is meaningful because it's part of something, part of a universe that's full of structure and complexity and change. Meaning doesn't come from contrast with nothing. It comes from participation in something, from connection to the larger existence of which we're a part. I think what this all comes down to is a fundamental shift in perspective. We're used to thinking of nothing as the default, the baseline, the neutral state from which something emerges and to which something returns. But maybe being is the default, existence is the baseline, somethingness is the neutral state. Maybe nothing is the anomaly, the impossibility, the thing that never was and never could be. And if we accept that, if we really internalize that shift in perspective, it changes how we think about everything. It changes how we think about the origin of the universe, because we're not looking for a cause of something emerging from nothing. We're looking for a mechanism by which one kind of something transforms into another kind of something. It changes how we think about death, because we're not fearing a return to nothing. We're accepting a transformation into different forms of something. It changes how we think about meaning, because we're not creating significance against a background of meaninglessness. We're participating in a universe that's inherently rich with structure and pattern and information. And maybe this is why the question of nothing has fascinated philosophers and scientists for so long, why we keep coming back to it, why we can't quite let it go. Because understanding nothing, or understanding that nothing is impossible, is a way of understanding something, of understanding existence, of understanding being itself. Nothing is the mirror that reflects everything, the negative space that defines the positive, the absence that makes presence visible. And if the mirror is impossible, if the negative space doesn't exist, if the absence is actually a presence, then everything changes. Everything becomes richer, denser, more complex, more necessary. Let me share one more thought, one more angle on this. In Zen Buddhism, there's a famous koan. What was your original face before you were born? It's a question that seems to point to nothing, to non-existence, to the void before being. But the point of the koan isn't to answer it literally, it's to break through ordinary thinking, to realize that the question is based on false assumptions. There was no nothing before you were born. There was something, always something. The universe existed. Matter and energy existed. The potential for your existence existed. Your original face is the face of the universe, the face of existence itself, because you're not separate from it, you're part of it, you've always been part of it, even before the specific configuration of atoms, that is, you came together. And that's true for all of us. We're not things that emerged from nothing and will return to nothing. We're patterns in something, temporary configurations of the universal somethingness, waves on an ocean that never was and never will be empty. The ocean is always full, always moving, always creating new waves and dissolving old ones. And we're those waves, and the ocean is existence, and nothing is impossible. I realize I've gone on for quite a while, circling around this question from different angles, approaching it from physics and philosophy and cosmology and consciousness. But I think that's appropriate, because nothing, or rather the impossibility of nothing, is one of those fundamental questions that touches everything, that connects to everything, that illuminates everything. Understanding that nothing might be impossible helps us understand what the universe is, what we are, what existence means. And I don't want to pretend I've answered every question, resolved every paradox, explained every mystery. I haven't. There's still so much we don't know. We don't know why the laws of physics are what they are. We don't know if there are other universes with different laws. We don't know how consciousness emerges from physical processes. We don't know what happened before the Big Bang. We don't know what the most fundamental level of reality is. These are open questions, active areas of research, ongoing mysteries. But what I hope I've shown is that nothing, the concept we thought was so simple, so straightforward, so obvious, is actually one of the most complex, most subtle, most impossible things we could imagine. Nothing isn't simple. It's not the default. It's not the baseline. Something is simple Existence is the default, being is the baseline. And once we understand that, once we really grasp that nothing might be impossible, it changes everything. It changes physics because we realize that the vacuum isn't empty, that empty space is full of structure and energy and possibility. It changes cosmology because we stop asking why something exists and start asking what kind of something exists and how it evolves and transforms. It changes philosophy because we recognize that being is fundamental and nothing is derivative if it exists at all. It changes how we think about ourselves because we're not isolated islands of being in a sea of nothing. We're interconnected parts of a vast something that's been here all along and will continue in different forms forever. And you know what's really beautiful about this? It means that fundamentally, at the deepest level, reality is generous. It's full, it's abundant, it's overflowing with existence. The universe doesn't withhold being, doesn't ration existence, doesn't make something a scarce resource against a background of nothing. Something is everywhere, always, in every form and configuration. Being is the gift that keeps on giving, the fountain that never runs dry, the reality that never wasn't. So when you look at the night sky, when you see the stars and galaxies and vast expanses of space, don't think of those as emptiness. Don't think of those as nothing. Think of them as full of quantum fields and virtual particles and dark matter and dark energy and all sorts of things we can detect and things we haven't detected yet. Think of space as a plenum, not a void, as a something, not a nothing. Because nothing, true nothing, doesn't exist, can't exist, might be fundamentally necessarily beautifully impossible, and maybe that's the deepest truth we can know about the universe. Not that something exists instead of nothing, but that nothing was never really an option, never really a possibility, never really a meaningful alternative. Something just is. Existence just happens. Being just be. And we're part of it. We're expressions of it. We're the universe waking up to itself and realizing that nothingness, that most basic, most fundamental, most obvious concept might actually be the one thing that isn't real. There's something profoundly reassuring about that, don't you think? In a world where everything changes, where nothing stays the same, where we're all temporary and fragile and mortal, it's good to know that existence itself is stable, is necessary, is impossible to eliminate. We're part of something that can't become nothing, that won't become nothing, that never was nothing. We're patterns in the eternal somethingness of reality. And even when our particular pattern dissolves, the somethingness remains, taking new forms, creating new patterns, continuing the endless dance of existence. And that, I think, is why nothingness might be impossible. Not because of any one reason, not because of any single principle or law or argument, but because of all of them together, because of the deep structure of reality itself, because of what existence is at its most fundamental level. Nothing is impossible because something is necessary. Nothing is impossible because being is inevitable. Nothing is impossible because at the end of the day, there's nowhere for nothing to be, nothing for nothing to be in, no time for nothing to exist, no space for nothing to occupy. Nothing is impossible because everything is something, and something is all there is, all there was, and all there ever will be. Now, let's move on to another theory for you to reflect on. I've been thinking a lot about choice lately, about this feeling we all have every single day that we're making decisions, real decisions, choices that matter and that come from us, from some essential part of who we are. You wake up in the morning and you decide whether to hit the snooze button or get up. You choose what to have for breakfast, what clothes to wear, whether to take the highway or the back roads to work. And in each of these moments, there's this sensation, this unmistakable feeling that you could have done otherwise, that the universe hung there for a second, waiting for you to make your choice. And then you made it, and reality split in the direction you chose. It feels real. It feels like the most real thing about being human, actually. This sense that we're authors of our own actions, captains of our own ships, free agents navigating through a world of possibilities. But what if I told you that this feeling, this bedrock sensation of agency and choice, might be one of the most elaborate illusions ever produced by the human brain? What if the quantum revolution in physics, combined with what we've learned from neuroscience, suggests something far stranger and more unsettling about the nature of will and choice? What if free will, as we understand it, as we experience it, is neither fully real nor fully illusory, but something caught in between, something quantum? And that's where things get interesting, right? Because this isn't just some abstract philosophical puzzle that academics debate in dusty offices. This is about you. This is about every decision you think you've ever made, every choice you've agonized over, every moment where you felt proud of choosing the right path or guilty about choosing the wrong one. It's about whether that feeling of responsibility, of agency, of being the one in control corresponds to anything real in the physical universe. And what quantum mechanics has revealed over the past century, combined with what neuroscience has discovered about how our brains actually make decisions, well, it paints a picture that's simultaneously more beautiful and more disturbing than most people realize. You see, we've lived most of human history with this intuitive sense that we're somehow separate from the mechanical universe around us. The rocks and rivers and planets follow laws, sure, but we're different. We have this special thing called consciousness, this mysterious capacity for choice. We can weigh options, consider consequences, deliberate, and then decide. And in that moment of decision, something genuinely new enters the universe, something that wasn't determined by the prior state of things. That's the intuition anyway. That's what it feels like from the inside. But the problem is that this intuition was formed long before we understood anything about the physical substrate of thought, long before we knew about neurons and quantum fields and the strange probabilistic nature of reality at its most fundamental level. Let's start with the simple stuff, with what we think we know from everyday experience. You're sitting in a coffee shop, right? And the waiter comes over and asks what you'd like. You look at the menu. There's coffee and tea, pastries and sandwiches, endless possibilities. And in that moment, you feel completely free to choose any of them. Nothing is forcing you. No one has a gun to your head. The universe seems to be presenting you with genuine options, real alternatives, and you get to pick. So you deliberate for a moment. Maybe you think about whether you've had too much caffeine already. Maybe you remember that the croissants here are particularly good, and then you decide, I'll have a cappuccino and a croissant, please. And in that moment, it feels like you could have chosen differently. You could have had the tea. You could have had nothing at all. The choice was yours, and it was real. That's the experience. That's what we call free will in its most basic, intuitive sense. But here's the thing, and this is where we need to start pulling at the threads. What actually happened in your brain during those few seconds of deliberation? Well, we know from neuroscience that your brain is an enormously complex network of about 86 billion neurons, each connected to thousands of others, all firing in intricate patterns, all governed by the laws of physics and chemistry. Electrical signals cascade through neural pathways, neurotransmitters bind to receptors, ion channels open and close, and somehow, out of all this physical activity, a decision emerges. You feel like you made the choice, like there was a you, a unified self, standing somehow above all this neural machinery and directing it. But what if that's not quite right? What if the you that feels like it's choosing is actually a kind of narrator, a story that the brain tells itself about what's happening, rather than the author of what's happening? There's this famous experiment, conducted by a neuroscientist named Benjamin Libet back in the 1980s. And it really shook a lot of people when they understood what it implied. Libet had people sit in front of a clock face with a dot moving around it, like a second hand, but faster. And he asked them to do something very simple, to flex their wrist whenever they felt like it, spontaneously, freely, whenever they chose. But he was measuring two things. He was measuring their brain activity using electrodes on their scalp, and he was asking them to note the exact moment when they first became aware of their intention to move, when they first felt the urge to flex their wrist. And what he found was strange, really strange. The brain activity that preceded the movement, what he called the readiness potential, started building up in the motor cortex about 550 milliseconds before the actual movement. But the conscious awareness of intending to move, the feeling of deciding to flex your wrist, that only came about 200 milliseconds before the movement, which means that the brain had already started preparing the action a third of a second before you consciously decided to do it. Now, I mean, that's unsettling, isn't it? It suggests that the conscious experience of making a decision, the feeling of free will, comes after the brain has already committed to a course of action. Your consciousness isn't the author of the decision. It's more like a spectator that gets informed about the decision slightly before it happens, and then it takes credit for it. It feels the decision as if it originated from the conscious self, but really the decision bubbled up from unconscious neural processes that you have no direct access to. And that raises this uncomfortable question, right? If the decision is already made before you're consciously aware of making it, in what sense did you make it at all? In what sense was it free? But that's just the neuroscience angle, and we'll come back to it in more depth, because there's another piece to this puzzle, another revolution in our understanding of reality that happened a bit earlier in the 20th century. And it comes from physics, from quantum mechanics specifically. And this is where things get really interesting, where the story gets complicated in ways that might actually rescue free will, or at least rescue something like it, or maybe make the whole question more subtle than we thought. See, before quantum mechanics came along, the universe was thought to work like a giant clockwork mechanism. This was the view that emerged from Newton's laws of motion and gravitation. If you knew the position and velocity of every particle in the universe at one moment in time, you could, in principle, calculate exactly where every particle would be at any future moment. The universe was deterministic, completely determined by its initial conditions and the laws of physics. There was no room for chance, no room for genuine novelty, no room for freedom. Everything that would ever happen was already implicit in the state of things at the Big Bang. This idea was captured perfectly by the French mathematician Pierre-Simon Laplace, who imagined a hypothetical superintelligent being, now called Laplace's demon, that knew the precise position and momentum of every atom in the universe. For this demon, Laplace said, nothing would be uncertain, and the future would be just as clear as the past. The whole history of the universe would be laid out like a movie reel, already shot, just waiting to be played. And if that's true, if classical determinism is the whole story, then free will is dead on arrival, right? Your brain is made of atoms, atoms that follow the laws of physics, atoms whose behavior is completely determined by prior states. Your decision to have coffee instead of tea wasn't really a decision at all. It was an inevitable consequence of the prior state of your brain, which was an inevitable consequence of the state before that, going all the way back to the initial conditions of the universe. You feel like you're choosing, but really you're just a complex machine playing out a script that was written 13.8 billion years ago at the moment of the Big Bang. That's the deterministic nightmare. That's what kept philosophers up at night for centuries, this sense that maybe we're all just puppets dancing on strings made of physical law. But then, in the early 20th century, something remarkable happened. Physicists started looking closely at atoms and subatomic particles, and they discovered that the neat, deterministic clockwork of Newtonian physics breaks down at the smallest scales. Quantum mechanics emerged, and with it came a kind of irreducible randomness, an indeterminacy that seems to be woven into the very fabric of reality. And at first, some people thought, aha, here's where free will comes in. The universe isn't deterministic after all. There's genuine randomness, genuine unpredictability, and maybe that's where our freedom lives. But it's not that simple. It's never that simple. Let me explain what quantum mechanics actually says, because it's important to get this right. At the quantum level, particles don't have definite properties until they're measured. An electron doesn't have a precise position and momentum simultaneously. Instead, it exists in what's called a superposition of possible states, a kind of blurry cloud of probability. The mathematics of quantum mechanics, the Schrödinger equation, describes how this cloud of probability evolves over time and that evolution is completely deterministic. The wave function, as it's called, evolves according to precise mathematical rules. But here's the weird part. When you actually measure the electron's position, when you try to observe where it is, the wave function collapses. The electron suddenly has a definite position, and which position it ends up with, which of the many possibilities becomes actual, that's random. Truly random, not just unpredictable because we lack information, but fundamentally random. There's no hidden variable determining which outcome you'll get. The universe itself doesn't know until the measurement happens. This is what's called quantum indeterminacy, and it's one of the most profound and strange discoveries in the history of science. Einstein hated it. He famously said that God doesn't play dice with the universe. But experiment after experiment has confirmed it. Reality, at its most fundamental level, is probabilistic, not deterministic. There are multiple possible futures, and which one becomes actual is a matter of chance, not predetermined by the past. So does this save free will? Well, not obviously, because randomness isn't freedom. If your decisions are random, they're not controlled by you. They're just, well, random. Imagine if every time you tried to make a choice, your brain flipped a quantum coin and did something unpredictable. That wouldn't feel like freedom. That would feel like chaos, like a loss of control. True free will, the kind we feel like we have, isn't just the absence of determinism. It's the presence of agency, the sense that our choices reflect our desires, our reasons, our values. It's the feeling that we are the authors of our actions, not that our actions are random events that just happen to occur in our brains. And that's the puzzle, you see. If the universe is deterministic, there's no room for free will because everything is already determined. But if the universe is random, there's also no room for free will because random events aren't controlled by anything, they just happen. So where does that leave us? Are we forced to choose between being machines and being random number generators? Is there no third option? No way to make sense of the intuition that we're genuinely making choices? Well, here's where it gets really interesting, where we need to dig deeper into what quantum mechanics might actually mean for free will. Because there's a lot more to the quantum story than just randomness. There's something called quantum entanglement, where particles can be correlated in ways that seem to transcend space and time. There's the measurement problem, the question of what it means for a wave function to collapse, and whether consciousness plays a role in that collapse. There's the possibility, explored by some physicists, that quantum effects might be relevant in the brain, that the mind might be doing something quantum mechanical that gives rise to consciousness and maybe even to free will. Let's start with that idea because it's probably the most directly relevant to our question. In the 1990s, a physicist named Roger Penrose and an anesthesiologist named Stuart Hameroff proposed a controversial theory about consciousness. They suggested that consciousness isn't just a product of classical neural activity, of neurons firing in patterns. Instead, they proposed that quantum effects in tiny structures inside neurons, called microtubules, might be crucial for consciousness and possibly for free will. The idea is that these microtubules can maintain quantum superpositions, quantum indeterminacy, for long enough that they could influence neural processing. And in the moment of making a decision, the quantum superposition collapses in a way that's influenced by, well, something. Maybe by consciousness itself. Maybe by some kind of quantum orchestration that's neither deterministic nor random, but something in between. Now, I should be clear. This theory, called orchestrated objective reduction, or ORCH-OR for short, is highly controversial. Most neuroscientists are skeptical of it. The brain is warm and wet and noisy, and most physicists think that quantum coherence, the delicate state where quantum effects matter, would be destroyed almost instantly in that kind of environment. There's a process called decoherence where quantum systems interacting with their environment lose their quantum properties and start behaving classically. And the brain seems like the worst possible place to maintain quantum coherence. It's like trying to keep a soap bubble intact in a hurricane. But, and here's the thing, some recent research has found hints that quantum effects might persist in biological systems longer than we thought. There's evidence of quantum coherence in photosynthesis, in the way that plants capture light energy. There are suggestions that birds might use quantum entanglement in their navigation systems, in the chemical reactions in their eyes that allow them to sense the Earth's magnetic field. So maybe, just maybe, the brain is doing something quantum too. Maybe evolution found a way to harness quantum effects for information processing. It's not proven. It's not even widely accepted, but it's not ruled out either. And if it's true, if the brain is somehow using quantum mechanics in its decision-making processes, what would that mean for free will? Well, it's complicated. On one hand, it would mean that our decisions aren't just the result of classical deterministic processes playing out in neural networks. There would be genuine indeterminacy, genuine openness in the decision-making process. The future wouldn't be fully determined by the past. But on the other hand, if that indeterminacy is just quantum randomness, we're back to the problem we had before. Random isn't free. Random is just random. Unless, and this is where Penrose and Hameroff get really speculative, unless the collapse of the quantum wave function, the moment when possibility becomes actuality, is somehow guided by consciousness itself. Unless consciousness isn't just an epiphenomenon, a byproduct of brain activity, but is actually playing an active role in collapsing wave functions, in choosing which possibility becomes real, that would be extraordinary. That would mean that consciousness is doing something that's neither determined nor random, but something else entirely, something that we don't have a good name for, something like genuine agency. But how would that work? How could consciousness influence quantum wave function collapse? And what even is consciousness that it could do such a thing? These are some of the deepest and most difficult questions in all of science and philosophy. They're part of what's called the hard problem of consciousness, the question of why and how physical processes in the brain give rise to subjective experience, to the feeling of what it's like to be you. And nobody really knows the answer. We have theories, lots of theories, but no consensus, no solution that everyone agrees on. What we do know is that consciousness is strange. It's not like anything else in the physical universe. When you see the color red, there's something it's like to see red. There's a subjective quality to the experience, what philosophers call qualia. And that subjective quality doesn't seem to be captured by any description of the physical processes happening in your brain. You could, in principle, know everything about the neural activity, the patterns of firing, the neurotransmitters, the whole physical story, and still not know what it's like to see red. That's the hard problem. And it's why some philosophers and scientists think that consciousness might be something fundamental, something that's not fully explained by the physics we know, something that might require new physics or a new understanding of the relationship between mind and matter. And if consciousness is something fundamental, if it's not just a complicated way that atoms can be arranged, but something more basic than that, then maybe, just maybe, it could play a role in quantum mechanics that we haven't understood yet. There's an interpretation of quantum mechanics, actually, that takes this seriously. It's called the von Neumann-Wigner interpretation, named after the mathematician John von Neumann and the physicist Eugene Wigner. And it suggests that the collapse of the wave function requires consciousness, that until a conscious observer looks at a quantum system, it remains in superposition. And when consciousness interacts with it, the wave function collapses and reality becomes definite. Most physicists don't accept this interpretation. They think it's too anthropocentric, too focused on human consciousness, as if we're special in the universe. And there are other interpretations of quantum mechanics that don't require consciousness at all. The Copenhagen interpretation says that measurement, not necessarily conscious measurement, causes collapse. The many worlds interpretation says there's no collapse at all, that every quantum possibility actually happens. But in different branches of reality, different parallel universes. Decoherence theory explains how quantum systems interacting with large environments lose their quantum properties without any special role for consciousness. So the truth is, we don't know. We don't know if consciousness plays a special role in quantum mechanics. We don't know if quantum mechanics plays a special role in consciousness. And we certainly don't know if any of this rescues free will from the pincer attack of determinism and randomness. But the fact that we don't know, the fact that there are these deep mysteries at the intersection of physics and consciousness and choice, that tells us something important. It tells us that the question of free will is more open than we might have thought. It's not a settled question. It's not something where science has given us a clear answer that we just need to accept, no matter how uncomfortable it makes us. Let me take you deeper into the neuroscience side of things, because there's a lot more to say about what actually happens in the brain when we make decisions. The Libet experiment that I mentioned earlier, the one showing that brain activity precedes conscious intention, it's been replicated many times and extended in interesting ways. There are studies using fMRI scanners that can predict someone's decision up to 10 seconds before they're consciously aware of making it, just by looking at patterns of activity in certain brain regions. 10 seconds, that's an eternity in brain time. It suggests that the decision is brewing in the unconscious depths of the brain long before the conscious mind has any idea what's going to happen. But let's be careful about what this means. It doesn't necessarily mean that free will is an illusion. It means that the conscious experience of making a decision comes late in the process. that there's a lot of unconscious processing happening before we become aware of our intentions. But maybe that's okay. Maybe the unconscious parts of the brain are still us. After all, it's not like there's a little homunculus, a little person sitting in your head making decisions, and then all this other neural machinery that's separate from the real you. The whole brain is you. The unconscious processes, the automatic responses, the gut feelings, the intuitions that bubble up, they're all part of your decision-making system. They're all you. And this is important because it points to a different way of thinking about free will, one that doesn't require some magical ability to transcend the laws of physics. It's called compatibilism, and it's the view that free will is compatible with determinism. The idea is that free will isn't about whether your decisions are determined by prior causes. Of course they are. Everything in the physical universe is determined by prior causes. The question is, what kind of causes are determining your decisions? Are they internal or external? Are they your own desires, beliefs, values, and reasoning processes? Or are they external constraints like someone holding a gun to your head? When you choose the coffee in the coffee shop, sure, that choice is determined by your brain state, which is determined by your prior experiences, your genetics, your neural wiring, all the way back. But those are your experiences, your neural wiring. The decision flows from who you are. It reflects your preferences and values. And that, the compatibilist says, is what freedom is. Freedom isn't the absence of causation. It's causation of the right kind. Causation that goes through your own psychological processes rather than bypassing them. And I think there's something appealing about that view, something that captures an important intuition. When we care about whether someone acted freely, what we're usually asking is whether they acted from their own desires and beliefs, whether they had alternatives available to them, whether they could have done otherwise if they had wanted to. We're not asking whether their decision violated the laws of physics. We're asking whether it was coerced or autonomous, constrained or open. But there's a problem with compatibilism, a deep problem that's hard to shake. If everything is determined by prior causes, then your desires and beliefs and values, the very things that the compatibilist says make your actions free, well, those are determined too. You didn't choose to have those desires. You didn't choose your personality, your temperament, your ways of seeing the world. Those were given to you by your genes and your upbringing and your experiences, none of which you chose. So in what sense is a decision that flows from those unchosen desires and beliefs really yours? In what sense is it free? It's like, imagine you're a computer running a program. The program has rules for how to respond to inputs, and when it receives an input, it processes it according to those rules and produces an output. The program is doing exactly what it was designed to do, but would we say the program is acting freely? Would we say it's making choices, or is it just executing code? And if you're like that program, if your brain is just executing code that was written by evolution and refined by experience, code that you didn't choose and can't ultimately control, then are you really free? This is where the quantum uncertainty comes back into the picture, but in a different way. See, even if quantum effects aren't directly relevant in the brain, even if consciousness isn't collapsing wave functions, the mere fact that the universe is fundamentally indeterministic might matter for free will in a subtle way. Because if determinism is false, if the future isn't completely determined by the past, then there's a sense in which the universe is open, genuinely open. Multiple futures are possible, not just epistemically, not just because we don't know which will happen, but ontologically because reality itself hasn't decided yet. And maybe in that openness, in that indeterminacy, there's room for something like agency. Not agency that violates physics, not some spooky power to make atoms do things they wouldn't otherwise do, but agency that's compatible with physics, that works through physics, that takes advantage of the fundamental openness that quantum mechanics reveals. Maybe when you make a decision, what's really happening is that the quantum indeterminacy that's everywhere in the universe, in every atom, in every quantum field, maybe that indeterminacy is being organized, channeled, shaped by the incredibly complex self-organizing system that is your brain. And the pattern that emerges, the decision that crystallizes out of all that quantum uncertainty, reflects your history, your values, your reasons, even though it wasn't predetermined. I know that sounds vague, and maybe it is vague. Maybe we don't yet have the conceptual tools to make it precise. But there's something intuitive about it. something that resonates. It's the idea that you're not separate from the physical universe, not some ghost in the machine, but you're a pattern in the universe, a complex, self-organizing pattern that processes information and responds to its environment, and in doing so, participates in the universe's creation of the future. You're not outside the system, controlling it like a puppet master. You're inside the system, you are part of the system, and your decisions are the system's way of deciding what to do next in this particular region of space and time. But let's push on this a bit more, because there's another wrinkle in the quantum story that we need to consider. It's the question of quantum entanglement and non-locality, and it raises some really fascinating and bizarre possibilities for how consciousness and choice might work. Quantum entanglement is when two particles become correlated in such a way that measuring one instantly affects the other, no matter how far apart they are. Einstein called it spooky action at a distance, and he thought it was evidence that quantum mechanics was incomplete, that there had to be some hidden variables we weren't seeing. But experiments, especially the famous experiments by Alain Aspect in the 1980s, confirmed that entanglement is real. The universe really does have these non-local correlations that seem to transcend space. Now, what does this have to do with free will? Well, think about it. If quantum systems can be correlated across space, if measuring one can instantly affect another, maybe consciousness, if it's doing something quantum, could be correlated in weird ways too. Maybe the sense of agency, the sense that you're making a choice, is connected to quantum processes happening throughout your brain, processes that are entangled with each other in ways that create a kind of unity, a binding of information that gives rise to the unified sense of self. And maybe in the moment of decision, that entangled quantum state is collapsing in a coordinated way that reflects your accumulated history and values, not deterministically, but not randomly either. Something in between, something holistic, something that we might call will. I know this is getting pretty speculative, pretty far out there, and I want to be clear that this is not established science. This is philosophy informed by physics, thinking about what might be possible given what we know about quantum mechanics and consciousness. Most neuroscientists think consciousness is entirely classical, that you don't need quantum mechanics to explain it. And they might be right, but the fact is, we don't understand consciousness. We don't know how the brain gives rise to subjective experience. And as long as that's true, as long as the hard problem of consciousness remains unsolved, we can't rule out that quantum mechanics plays a role. And there's another angle to this whole puzzle that I think is really important, something that has to do with complexity and emergence. See, one of the remarkable discoveries of the last few decades is that complex systems with many interacting parts, can exhibit behaviors that are more than the sum of their parts. They can self-organize, create patterns, exhibit properties that aren't present in any of the individual components. This is called emergence, and it's everywhere in nature. The wetness of water emerges from molecules that individually aren't wet. The solidity of a table emerges from atoms that are mostly empty space. Life emerges from chemistry. Consciousness emerges from neurons. And maybe, just maybe, free will is an emergent property too. Not something that exists at the level of atoms and particles, not something that violates physics, but something that emerges at the level of the whole brain, the whole person, the whole self-organizing system that is you. At the lower level, at the level of neurons and synapses and maybe quantum processes, everything is either deterministic or random. But at the higher level, at the level of the integrated system, something new appears, something that we experience as choice, as agency, as will. This is tricky to think about clearly because we're so used to thinking in terms of bottom-up causation, the idea that everything that happens at higher levels is caused by what's happening at lower levels. Atoms cause molecules, cause cells, cause organisms. But in complex systems, there's also top-down causation, where the organization and structure at higher levels constrains and influences what happens at lower levels. Your beliefs and desires, your goals and plans, they're high-level features of your brain's organization. But they have causal power. They influence which neurons fire, which pathways are strengthened, which decisions are made. And that causal power, that ability of the high-level patterns to shape the low-level processes, that might be what freedom is. It's not freedom from physics. It's freedom within physics, freedom that arises from the special kind of organization that complex systems like brains can have. And that freedom is real, it's causally efficacious, even though it's ultimately grounded in and constrained by the lower-level physical processes. Just like the wetness of water is real and has causal effects, like making your clothes wet, even though it emerges from the interactions of molecules that aren't themselves wet. Now let's circle back to the interpretation of quantum mechanics called many worlds, because it has some really wild implications for free will that we should consider. The many worlds interpretation proposed by Hugh Everett in the 1950s says that there's no wave function collapse at all. Every quantum possibility that could happen does happen, but in different branches of reality, different parallel universes. When you measure an electron's position, and it could be here or there, both outcomes happen. The universe splits, and in one branch the electron is here, and in another branch it's there, and you, the observer, split too. There's a version of you that sees the electron here, and another version that sees it there. If many worlds is true, and a lot of physicists take it seriously because it's mathematically elegant and doesn't require any special collapse mechanism, then what does that mean for free will? Well, in one sense, it means every possible decision you could make, you do make, just in different branches. When you were deciding between coffee and tea, both choices happened. There's a universe where you chose coffee and another universe where you chose tea. So, in a way, you don't have to choose. All possibilities are realized. But that doesn't seem right, does it? Because you, the you that's here right now in this branch, you only experience one outcome. You chose coffee, not tea. You don't have access to the other branches, the other versions of yourself making different choices. So from your subjective perspective, from the inside, you still had to choose. The many worlds interpretation doesn't eliminate the experience of choice. It just multiplies it across branches. But there's something deeply strange about this. If all possibilities happen, then in what sense did you really choose? The version of you that chose coffee might think, I chose coffee because I prefer it. And the version that chose tea might think, I chose tea because I wanted to cut back on caffeine. Both versions have reasons, both feel like they chose freely. But from a God's eye view outside the branches, there was no single choice. Every outcome that was physically possible occurred. So maybe choice is just an illusion that arises from having a limited perspective, from being stuck in one branch and not seeing all the others. Or maybe the question is ill-posed. Maybe asking whether free will exists in a many worlds universe is like asking whether you chose to be in this particular branch. You didn't choose it. You're in all the branches, or rather, there are versions of you in all the branches, and each version experiences their branch as the only one. And each version feels like they chose freely because within their branch, their decision was the one that happened, the one that shaped their future. So free will, in a many worlds context, might be about which branch you experience, which version of yourself you are, rather than about making possibilities happen or not happen. And that brings us to a really deep question about identity, about what the self is. Because if there are multiple versions of you in different branches, all equally real, which one is the real you? Or are they all you? And if they're all you, then what does it mean to make a choice? What does it mean to be responsible for your actions? These questions don't have easy answers. They might not have answers at all in the sense that we usually think of answers, clear yes or no responses. They might be questions that reveal the limits of our concepts, the ways in which our everyday notions of self and choice and freedom don't map neatly onto the strange reality that physics reveals. Let's think about the subjective experience of making a decision. Really think about what it feels like from the inside, because I think that's where a lot of the mystery lies. When you're in the moment of choosing, when you're weighing options, deliberating, considering, there's a felt sense of openness, a sense that multiple futures are possible and you're in the process of determining which one will be actual. Time seems to slow down a little. You're aware of the alternatives, imagining how each would play out, how each would feel, and then at some point, one option just feels right. It clicks, and you go with it. But what's actually happening in that moment? What is the physical correlate of that subjective sense of deliberation and choice? Neuroscience tells us that it's an enormously complex process involving many brain regions. Your prefrontal cortex is evaluating options, weighing costs and benefits, considering long-term consequences. Your limbic system is generating emotional responses to the different options, giving you gut feelings about what you want. Your basal ganglia are involved in selecting actions, in initiating motor programs. And all of these regions are communicating with each other, sending signals back and forth, competing and cooperating until some kind of consensus emerges, some pattern of activity stabilizes, and that pattern is the decision. But here's the thing, you don't experience all that complexity. You don't feel the different brain regions arguing with each other. You feel like there's a unified you, a single self, considering the options and making a choice. And that unified self is, in a sense, a construction, a model that the brain creates to make sense of its own activity. The brain has to integrate information from many different systems that evolved at different times for different purposes, and present that information to consciousness as a coherent narrative. And part of that narrative is the sense that there's an I who is the author of decisions, who is in control. But what if that sense of control is at least partially an illusion? What if the brain makes decisions through a kind of distributed, parallel process, and then, after the fact, constructs a narrative in which a unified self made the decision? There's evidence for this from split brain patients, people who have had the connection between the two hemispheres of their brain severed to treat severe epilepsy. In these patients, the two hemispheres can process information independently, and sometimes they seem to have different intentions, different goals. One hand might reach for something while the other hand tries to stop it. And when you ask the patient why they did something, they'll confabulate, they'll make up a reason that sounds plausible, even though it's not the real reason. The verbal left hemisphere, which is the one that speaks, doesn't have access to what the non-verbal right hemisphere is doing, so it just makes up a story that makes sense. And if that's happening in split brain patients, maybe it's happening in all of us all the time. Maybe the sense that we're the authors of our actions, that we're choosing freely, is a story that the brain tells itself, a narrative constructed after the fact to make sense of decisions that are really made by non-conscious distributed processes. That's a pretty unsettling thought. It suggests that the self, the I, that feels so central to our experience might be more like a spokesperson, a PR department, than like a CEO making executive decisions. But even if that's true, even if the unified self is a construction, does that mean free will is an illusion? I'm not sure it does, because the constructed self is still real, in a sense. It's a real pattern of brain activity, a real organizing principle, and it has causal power. Your beliefs about yourself, your sense of identity, your narrative about who you are and what you value, these things influence your behavior. They shape which decisions the brain makes. So even if the self is a construction, it's a causally efficacious construction. It's not just an observer. It's part of the system that's making the decisions. And maybe that's enough. Maybe free will doesn't require some metaphysical magic, some ability to step outside the causal order of the universe. Maybe it just requires that your actions flow from your beliefs, desires, and values, that they're determined by who you are rather than by external forces. And even if who you are is itself determined by factors you didn't choose, genes and environment and all the rest, well, maybe that's okay. Maybe that's just what it means to be a finite being in a physical universe. But I want to push on this a bit more because there's a moral dimension to all this that we can't ignore. If free will is an illusion, if our decisions are determined by factors beyond our control, what does that mean for moral responsibility? Can we hold people accountable for their actions if they couldn't have done otherwise? Can we praise virtue or condemn vice if people are just doing what their brains were always going to make them do? This is a really old question, one that philosophers have wrestled with for millennia, and different philosophical traditions give different answers. Some say that moral responsibility requires libertarian free will, the ability to have done otherwise in an absolute sense, not determined by prior causes. If determinism is true, they say, then no one is truly responsible for anything. We might still need to have laws and prisons to protect society, but it would be unjust to punish people for something they couldn't help doing. Others, the compatibilists, say that moral responsibility only requires that your actions flow from your own desires and beliefs, that you weren't coerced or insane or ignorant of what you were doing. If you acted from your own reasons, then you're responsible, even if those reasons were themselves determined by factors you didn't control. The point of moral responsibility, they say, isn't to identify some metaphysical property of absolute freedom. It's to identify which people's behavior can be modified by incentives and social norms. We hold people responsible not because they could have done otherwise in some absolute sense, but because holding them responsible affects their future behavior and the behavior of others. And there's something pragmatic and sensible about that view. It preserves our practices of moral evaluation and responsibility without requiring any spooky metaphysics. But it does require accepting that moral responsibility is, in a sense, a useful fiction, a social practice, rather than a deep metaphysical truth. And some people find that unsatisfying. They feel like responsibility should be grounded in something more fundamental, in the real ability to choose freely. And this is where the quantum indeterminacy comes back. Because if there is genuine indeterminacy in the brain, if quantum effects are playing a role in decision making, then maybe we do have the ability to do otherwise. Maybe when faced with a choice, multiple outcomes are genuinely possible, not just epistemically but ontologically. The universe hasn't decided yet which outcome will happen. And maybe our consciousness, our agency, plays a role in determining which possibility becomes actual. Not by violating physics, but by being part of the physical process that selects among quantum possibilities. But here's the rub. If the selection among quantum possibilities is random, if it's not guided by anything, just the collapse of a wave function according to probability, then we're not any more responsible for the outcome than we would be if we rolled dice to make decisions. Randomness doesn't ground responsibility any better than determinism does. Maybe worse, actually, because at least with determinism, your actions reflect your character, your values, the kind of person you are. With pure randomness, they don't reflect anything. They're just chance. So if quantum mechanics is going to help with free will and moral responsibility, it can't just be that there's quantum randomness in the brain. There has to be something more, something that organizes or channels that randomness in a way that reflects the person's reasons and values. And that's where the theories about quantum consciousness, about quantum coherence in microtubules or whatever, they're trying to find a mechanism for that. They're trying to explain how the indeterminacy of quantum mechanics could be harnessed by consciousness in a way that produces genuine agency, not just determinism and not just randomness, but something in between. And I'll be honest, I don't know if that's possible. I don't know if the physics allows for it. It might be that we're stuck with the dilemma that the universe is either deterministic or random and there's no third option. But I also think we don't know enough yet to be sure. We don't understand consciousness. We don't understand the quantum to classical transition, how quantum systems become classical systems when they interact with their environment. We don't understand whether there are special circumstances, like maybe the conditions in the brain where quantum effects could be maintained and play a functional role. These are open questions, areas of active research, and we should be humble about declaring definitive answers. Let me shift gears a little and talk about something called the readiness potential and some more recent research that complicates the simple picture from the Libet experiments, because it turns out that the story is more nuanced than the brain decides before you're conscious of deciding. There have been follow-up studies that give people the option to veto their decision at the last second, to abort the action even after the readiness potential has started building up. And people can do that. They can change their mind. So the readiness potential doesn't guarantee that the action will happen. It's more like the brain is preparing for a possible action, getting ready. But the final go or no-go decision can still be influenced by conscious deliberation. And there's also research suggesting that the readiness potential might not be as specific as we thought. It might just reflect general preparatory activity, the brain revving up, rather than a commitment to a specific action. When you're about to make a spontaneous movement, your brain gets ready, but which movement you end up making might not be determined until later, until closer to the moment of conscious intention. So maybe the conscious mind does play a more significant role than the Libet experiment suggested. Maybe it's not just a passive observer, but an active participant in the decision-making process, even if it comes late in the game. This is important because it suggests that the neuroscience doesn't definitively rule out free will. It shows that decisions involve complex temporal dynamics, with unconscious processes coming first and conscious experience coming later. But it doesn't show that consciousness is irrelevant, that it's just along for the ride. Consciousness might be doing something important, even if it's not the sole author of decisions. It might be providing a kind of executive oversight, a way of integrating information from different systems and making final adjustments. It might be the place where reasons and values are brought to bear on decisions, where we step back and ask not just what we want to do, but what we should do. And that's a crucial distinction, because moral agency, the kind of agency that grounds responsibility, isn't just about making decisions. It's about making decisions for reasons, being able to evaluate your desires and impulses in light of your values and commitments. Animals make decisions. They choose food, mates, paths, but we don't usually think of them as morally responsible because their choices aren't mediated by reason in the way human choices are. They act on instinct and conditioning. Humans, on the other hand, can reflect on their actions, can ask whether what they want to do is what they ought to do, can override immediate impulses in favor of long-term goals or moral principles. And maybe that capacity for reflection, for reasoning about reasons, is what's essential for free will. Not the ability to make uncaused choices, not some quantum magic, but the ability to be guided by reasons, to act from values and commitments that you've reflected on and endorsed. That's what philosophers call autonomy, self-governance, and it might be the core of what we really care about when we talk about free will. But even autonomy, even the ability to act from reasons, is a complex capacity that depends on brain function, on having the right kind of cognitive architecture, the right kind of development and education. And not everyone has that capacity to the same degree. Some people have brain damage or developmental disorders that impair their ability to reason and reflect. Some people have been raised in environments so abusive or neglectful that they never developed a healthy sense of self or the ability to regulate their impulses. Are they less free? Are they less responsible? I think most of us would say yes, to some degree. We make allowances for people whose capacity for autonomous decision-making is compromised. We don't hold children fully responsible for their actions. We don't hold the severely mentally ill fully responsible. We recognize that responsibility comes in degrees, that it depends on having certain capacities, and that suggests that free will, whatever it is not a simple binary property that you either have or don't have. It's a complex capacity that admits of degrees that can be more or less developed, more or less compromised by various factors. And maybe that's the right way to think about it, not as a metaphysical puzzle about whether our actions are determined or random, but as a practical question about what capacities people have, what their cognitive and emotional resources are, and how those resources enable or constrain their ability to make thoughtful, autonomous decisions. There's a view in philosophy called semi-compatibilism, proposed by John Martin Fisher, that tries to capture this. It says that moral responsibility doesn't require the ability to do otherwise, doesn't require libertarian free will. What it requires is that your actions flow from a mechanism that's reasons responsive, a mechanism that responds appropriately to reasons and can be guided by your values. And even if that mechanism is deterministic, even if your actions are determined by prior causes, you can still be responsible as long as the right kind of mechanism is operating, as long as your actions are responsive to reasons in the right way. I find this appealing because it focuses on what seems to really matter for responsibility, which is whether people are sensitive to reasons, whether they can be guided by moral considerations, whether their actions reflect their values. It sidesteps the metaphysical puzzle about determinism and indeterminism and focuses on the psychology of decision-making. And from that perspective, the quantum stuff, the question of whether there's indeterminacy at the neural level, it might not matter much. What matters is the higher level structure, the way the brain processes information and responds to reasons. But I don't want to dismiss the quantum stuff too quickly, because there's something about it that still seems relevant, still seems to capture something important about the openness of the future. If the universe is fundamentally deterministic, if every event is determined by prior events all the way back, then in a sense, the future is already written. It's implicit in the past. And even if we can't predict it, even if we don't know what will happen, it's already fixed. There's only one possible future, the one that will actually occur. But if quantum mechanics is true, if there's genuine indeterminacy, then the future is open. Multiple futures are possible, not just epistemically, but really possible. The universe itself hasn't decided yet which will be actual. And I think that matters for how we think about ourselves and our place in the universe. If the future is already fixed, then we're just watching a movie that's already been filmed, even if we don't know how it ends. But if the future is open, then we're participants in creating it. Our decisions are part of the process by which the universe determines what happens next. And that seems to be what we feel from the inside. We feel like the future is open, like our choices matter, like we're genuinely contributing to shaping what happens. And if quantum mechanics is right, that feeling corresponds to something real about the universe, not just to our ignorance of what's determined. Of course, this still leaves the question of whether the quantum indeterminacy is just randomness, or whether it's something we can influence, something that responds to our agency. And I've gone back and forth on this because on one hand, physics seems to suggest it's just randomness, just probability. But on the other hand, we don't understand the relationship between consciousness and physics, between mind and matter. We don't know if consciousness is doing something in the quantum domain that we haven't detected yet, something that organizes the randomness in a way that reflects intentions and values. And there's a possibility, a speculative possibility, that's worth considering. Maybe consciousness isn't fundamental in the sense of being a separate substance or force. Maybe it's an emergent property of complex information processing, like most neuroscientists think. But maybe when information processing reaches a certain level of complexity and integration, when it becomes self-referential and reflective, it creates a kind of top-down causation that can influence the lower-level quantum processes, not by violating physics, not by adding some new force, but by constraining the space of possibilities in a way that selects for outcomes that align with the system's goals and values. This is getting pretty abstract, I know, but think of it this way. A living organism is a system that maintains itself far from equilibrium. It takes in energy and matter, uses them to maintain and reproduce its structure, and exports entropy to the environment. And in doing so, it creates order, it creates patterns that are highly unlikely from a purely physical perspective. The second law of thermodynamics says entropy increases, disorder increases, but life seems to violate that by creating order. Of course, it doesn't actually violate the second law because the organism is not a closed system. It's exporting entropy, increasing disorder in the environment more than it's creating order internally. But still, locally, it's creating order. It's organizing matter in highly specific ways. Now, maybe consciousness is doing something similar at the quantum level. Maybe it's not violating quantum mechanics, but it's harnessing the quantum indeterminacy, organizing it in a way that creates patterns that reflect the organism's goals and values. And those patterns, when they're complex enough and integrated enough, feel like will, like agency, like choice. They're not random because they're constrained by the structure and history of the system, but they're not determined either because they involve genuine quantum indeterminacy. They're something in between, something that emerges from the interaction of consciousness and quantum mechanics. I don't know if this is right. I don't know if it's even coherent. It might be that I'm just engaging in wishful thinking, trying to find a way to preserve free will in the face of physics that doesn't support it. But I also think it's worth exploring these possibilities, worth thinking carefully about what the relationship between mind and matter might be, because we don't have all the answers yet. We don't understand consciousness. We don't understand the foundations of quantum mechanics. And maybe in the gaps of our understanding, there's room for something like free will, not as a violation of physics, but as a natural consequence of the way consciousness and quantum mechanics interact in complex systems like brains. Let me bring this back to the everyday experience of choice, because ultimately that's what we care about. We don't care about abstract metaphysics for its own sake. We care because we want to understand what it means to be human, what it means to make choices, what it means to be responsible for our actions. And the experience of choice, the feeling of deliberating and deciding, is a central part of human life. It's part of what gives life meaning and structure. And here's the thing, even if free will is in some sense an illusion, even if our decisions are determined by factors we don't control or influenced by quantum randomness we can't guide, That doesn't change the experience. You still have to make choices. You still have to deliberate, to weigh options, to consider consequences. You still have to live with the outcomes of your decisions. And the quality of your life depends, to a significant degree, on the quality of your decisions, on whether you choose wisely or foolishly, whether you act from your values or against them. So in a practical sense, it doesn't matter whether free will is real in some ultimate metaphysical sense. What matters is that you take your choices seriously, that you reflect on what you value and try to act accordingly, that you take responsibility for your actions and their consequences. And that's something you can do regardless of whether the universe is deterministic or indeterministic, regardless of whether consciousness is quantum or classical, regardless of all the deep metaphysical questions we've been exploring. But at the same time, I think these questions matter because they shape how we think about ourselves and others. If we believe that people are genuinely free, that they have ultimate responsibility for their actions, we might be more inclined to judge harshly, to blame and punish without mercy. If we believe that people's actions are determined by factors beyond their control, their genes and environment and brain chemistry, we might be more compassionate, more understanding, more focused on rehabilitation than retribution. And that's a significant difference. It affects how we structure our legal system, our educational system, our social policies, and this is where the science and philosophy of free will connect to ethics and politics, because our beliefs about human nature, about whether people are free or determined, shape our moral and political intuitions. They shape what we think is just and unjust, what we think people deserve. And if the science is telling us that free will, at least in the libertarian sense, might not exist, that our decisions are largely shaped by factors we don't control, then maybe we need to rethink some of our assumptions about justice and responsibility. But we also need to be careful not to throw the baby out with the bathwater. Even if libertarian free will doesn't exist, even if our actions are determined or random or some complex combination, that doesn't mean we should abandon all notions of responsibility. Because responsibility serves important social functions. It helps regulate behavior. It encourages people to reflect on their actions. It maintains social trust. If we stopped holding people responsible for anything, if we treated everyone as mere victims of their circumstances or their brain chemistry, society would fall apart. So what we need is a nuanced view, one that recognizes the constraints on human agency, the ways in which our choices are shaped by factors we don't control, but that also recognizes the real capacities we have for reason and reflection, the ways in which we can shape our own character and behavior through effort and practice. We need a view that's informed by science, but doesn't reduce humans to mere machines or random quantum fluctuations. We need a view that preserves what's valuable about the concept of free will, the sense that we're agents who can make choices and shape our lives, while being realistic about the limits of that agency. And maybe that's where the quantum perspective is actually helpful, not because it proves free will exists, but because it shows that the universe is more open, more subtle, more mysterious than classical physics suggested. It shows that determinism isn't the whole story, that there's genuine indeterminacy at the foundations of reality. And even if that indeterminacy is just randomness, even if it doesn't give us the kind of ultimate control we might want, it still means the future is open in a real sense. It means that what happens is not already determined by the past. And that's something. That's a kind of openness, a kind of possibility that's worth recognizing and valuing. There's a thought experiment I want to share, something that might help illuminate the puzzle we're grappling with. Imagine a perfect duplicate of you, created atom by atom in exactly the same quantum state. This duplicate has all your memories, all your beliefs and desires, all your neural wiring, everything. And suppose this duplicate is placed in exactly the same situation you're in right now. Would the duplicate make the same choice you would make? If the universe is deterministic, the answer is yes, necessarily. The duplicate would have to make the same choice because everything about them and their situation is identical to you. But if quantum indeterminacy plays a role, if there's genuine randomness in neural processing, then the duplicate might make a different choice. The quantum dice might roll differently. But here's the question. If the duplicate makes a different choice, and it's just because of quantum randomness, does that mean either you or the duplicate is more free? It doesn't feel like it, right? It feels like the difference would be arbitrary, not meaningful. So the quantum indeterminacy by itself doesn't seem to give us what we want from free will. But maybe, if there's something about the way consciousness interacts with quantum processes, something that means the randomness isn't entirely random, but is biased or constrained by your reasons and values, then maybe the duplicate would tend to make the same choice you would, but not with certainty. There would be a probability distribution over possible choices, weighted by how aligned each choice is with your values and reasons. And that maybe is a kind of freedom, not absolute freedom, not the ability to do literally anything, but a constrained freedom, a freedom that reflects who you are while still being genuinely open. I'm speculating wildly now, I know. But I think speculation is valuable when we're dealing with questions at the edge of our understanding. We have to be willing to think creatively, to consider possibilities that might sound strange or even incoherent at first. Because the truth about consciousness and free will, if we ever find it, is likely to be strange, likely to challenge our preconceptions in deep ways. Let me think about this from another angle, from the perspective of what it means to be a self, an integrated subject of experience. One of the puzzles about consciousness is the binding problem. The question of how all the different streams of sensory information, all the different cognitive processes happening in parallel in the brain, get unified into a single coherent experience. But when you look at a red ball, your visual system is processing color information in one area, shape information in another, motion information in another, but you don't experience them separately. You experience a unified object, a red ball. How does that happen? How does the brain bind all that information together? There are various theories, but one possibility is that quantum coherence plays a role. Maybe the different neural processes become quantum entangled in a way that creates a unified quantum state, and that unified quantum state is what we experience as a single integrated consciousness. If that's true, then consciousness isn't just classical information processing. It's something quantum, something that involves the kind of holistic, non-local correlations that quantum entanglement provides. And if consciousness is quantum in that way, then maybe it has a special relationship to the quantum indeterminacy in the brain. Maybe the collapse of quantum superpositions is influenced by the unified conscious state, influenced by the integrated perspective of the subject. This is, again, highly speculative, but it's the kind of speculation that some serious scientists like Roger Penrose have engaged in. And I think it's worth taking seriously, not as proven fact, but as a possible direction for future research. Because we do need a theory of consciousness that explains how it relates to the physical brain. And if quantum mechanics is relevant, that would be a major discovery, a paradigm shift in how we understand the mind. Now, even if all of this is wrong, even if consciousness is entirely classical and free will is entirely illusory, I think there's still a sense in which the concept of free will is valuable, a sense in which it points to something real and important about human life. Because the experience of agency, the feeling of being a self who makes choices, is constitutive of what it means to be human. It's not just an add-on, not just a false belief we happen to have. It's deeply woven into our sense of identity, our relationships with others, our projects and commitments. We can't just decide to stop experiencing ourselves as agents. We can't just decide to stop deliberating and choosing. Even if we intellectually believe that free will is an illusion, we still have to live as if we have it. And maybe that's okay. Maybe the illusion, if it is an illusion, is a necessary one, a kind of user interface that the brain creates to help us navigate the world. Just like the visual system creates the illusion of a stable, continuous visual field, even though we're actually seeing in rapid snapshots with blind spots and saccades, the motor system creates the illusion of unified agency, even though decisions are made by distributed parallel processes. The illusion is functional. It works. It helps us make decisions and coordinate our actions in a complex, unpredictable environment. So perhaps the right attitude is not to despair about free will being an illusion, but to recognize it as a kind of necessary fiction, a story we tell ourselves that enables us to function as agents. And like any good story, it has truth to it, even if it's not literally true. It captures something real about the structure of human experience and the nature of human life. But I want to come back to the moral dimension one more time, because I think it's crucial. If we're going to revise our understanding of free will in light of neuroscience and quantum mechanics, we need to think carefully about what that means for morality, for justice, for how we treat each other. And I think the key insight is that responsibility is not all or nothing. It's not the case that either people are completely free and completely responsible, or they're completely determined and not responsible at all. Reality is more nuanced than that. People have varying degrees of capacity for rational deliberation, varying degrees of self-control, varying degrees of understanding of moral norms, and these capacities can be enhanced or impaired by various factors: brain development, education, mental health, stress, fatigue, substances, social context. When we hold people responsible, what we're doing is recognizing their capacity for reason and trying to engage with them as rational agents. We're saying, you have the ability to understand why this action was wrong, to learn from this experience, to do better in the future. And that's appropriate when someone genuinely has that capacity. But when they don't, when their capacity is severely impaired, it's not appropriate. It's not just or effective. So a scientifically informed view of free will should make us more nuanced in our moral judgments. It should make us ask not just, did this person do a bad thing, but what was their mental state? What were the circumstances? What capacities did they have? What factors were constraining their ability to choose well? And it should make us focus more on forward-looking considerations, on prevention and rehabilitation, rather than backward-looking considerations of desert and retribution. Not because no one deserves anything, but because our main goal should be to reduce harm and promote well-being, not to inflict suffering on those who are deemed blameworthy. And here's where I think the quantum perspective might actually be helpful, even if it doesn't give us libertarian free will. If the universe is fundamentally indeterministic, if there's genuine openness about the future, then there's always a chance for change. People are not fixed entities with immutable natures. They're complex, dynamic systems that can evolve and develop. The patterns of neural connectivity that shape behavior can be modified through experience and effort. Habits can be broken, new skills learned, perspectives shifted. And if there's quantum indeterminacy involved, then the future is truly open. The past doesn't fully determine who someone will become. There's always room for surprise, for growth, for redemption. That's a hopeful thought, I think. It means that no one is beyond help, no one is irredeemably bad, no one is trapped by their past. There's always the possibility of change, of making different choices, of becoming a different kind of person. And that's worth valuing, worth protecting, worth building our social institutions around. Let me try to bring all these threads together to synthesize what we've been exploring. We started with the ordinary experience of choice, the feeling that we're free agents making decisions that matter. Then we looked at the challenges to that intuition from neuroscience, which shows that conscious decisions are preceded by unconscious neural activity, and from classical physics, which suggests that the universe is deterministic. And we then explored quantum mechanics, which introduces genuine indeterminacy, but also the question of whether that indeterminacy is just randomness or something that consciousness can influence. We considered various interpretations of quantum mechanics and their implications for free will. We looked at the possibility that quantum effects might be relevant in the brain, though that's controversial. We examined philosophical views about free will and responsibility, from libertarianism to compatibilism to hard determinism. And we thought about the moral and practical implications of these different views. And where does that leave us? I think it leaves us with uncertainty, with mystery, but also with a richer understanding of the question. We can't say definitively whether free will exists or not, because the answer depends on what we mean by free will, on which scientific theories are correct, on philosophical questions that remain unresolved. But we can say that the experience of agency is real and important, that the capacity for rational deliberation and self-governance is real and important, and that these things matter for how we live our lives and how we structure our society, regardless of the ultimate metaphysical truth about determinism and indeterminacy. And maybe that's the most important lesson. Maybe the question of free will is not primarily a scientific or metaphysical question, but an existential and ethical one. It's a question about how we understand ourselves, how we relate to each other, how we take responsibility for our lives and our communities. And from that perspective, the answer is not something we discover through physics or neuroscience, but something we create through how we choose to live, how we choose to treat each other, how we choose to think about agency and responsibility. Because here's the paradox: even if free will is an illusion, even if our choices are determined or random or some combination, we still have to make choices. We can't opt out of decision making. We can't wait for science to tell us what to do. We have to deliberate, we have to choose, we have to act. And in acting, we shape the world. We create patterns, we influence others, we leave traces. And those traces matter. They have consequences that ripple out in ways we can't fully predict or control. So maybe the deepest truth about free will is not whether it's real or illusory, but that we're embedded in a universe that's unfolding in time, a universe where the future is not yet determined, not yet actual, and we're part of the process by which it becomes determined, by which possibility becomes actuality. We're not separate from that process, not outside observers. We're inside it, we're part of it, and our decisions, our actions, our thoughts and intentions, they're all part of how the universe decides what to do next, at least in this small corner of space and time where we exist. And maybe that's enough. Maybe that's all we need. Not some grand metaphysical freedom that transcends physics, but the ordinary, everyday capacity to think and choose and act, to respond to reasons, to shape our lives through our decisions. That capacity is real. It's not an illusion. It's part of what makes us human, and it's what we should focus on, what we should cultivate and protect and value. The quantum mechanics, the neuroscience, the philosophy, they all help us understand the context in which this capacity operates. They show us that the universe is stranger than we thought, that the relationship between mind and matter is more subtle and mysterious than we imagined. They challenge our naive intuitions about how choice works, but they don't eliminate the reality of choice. They just help us see it more clearly, see it for what it really is, a complex, emergent process that arises from the interaction of billions of neurons, shaped by evolution and experience, constrained by physics but not fully determined by it, producing the remarkable phenomenon of a conscious subject navigating through an uncertain world, making decisions that matter, creating meaning and value through the act of choosing. And that, I think, is beautiful. It's beautiful that we exist at all, that matter can organize itself into conscious beings who can reflect on their own existence, who can wonder about the nature of choice and freedom and reality. It's beautiful that we're part of this vast, ancient, evolving cosmos, this quantum mechanical dance of particles and fields and forces, and that somehow in us, the universe has become aware of itself, has begun to question itself, to explore its own foundations. We're not separate from nature. We're nature's way of exploring itself, understanding itself, perhaps even choosing itself. So yes, free will might be an illusion in some sense. The feeling that we could have done otherwise, the feeling that our choices are uncaused or that we're the ultimate source of our actions, that might not correspond to reality. But the capacity to deliberate, to respond to reasons, to act from our values, to shape our lives through our decisions, that's real. That's not an illusion. That's what we are. That's human agency. And it's worth celebrating, worth protecting, worth taking seriously. And as for the quantum mechanics, well, maybe it plays a role, maybe it doesn't. Maybe consciousness is doing something quantum that we haven't understood yet, maybe it's not. But either way, the mystery remains. The mystery of how subjective experience arises from objective matter, how quality emerges from quantity, how meaning arises in a universe of physical processes. And that mystery is part of what makes life interesting, part of what makes the question of free will so compelling. Because it's not just about whether we're free, it's about what it means to be conscious, to be alive, to be a subject of experience in a world of objects. And maybe the answer is that we'll never fully understand it, that consciousness will remain mysterious, that the relationship between mind and matter will always have something ineffable about it. But that doesn't mean we should stop asking, stop exploring, stop wondering, because the act of wondering, the act of questioning, that's part of what it means to be human. That's part of how we exercise our agency, by directing our attention, by choosing what to think about, by deciding what questions matter. So I'll end where I began, with the ordinary experience of choice, the feeling of standing at a crossroads with multiple paths ahead, the sense that what we decide matters, that we're contributing to creating the future, not just watching it unfold. That experience might be more complex than we thought, shaped by factors we don't fully control, constrained by laws we don't fully understand. But it's real. It's part of the texture of human life. And whether it's grounded in quantum indeterminacy or emergent complexity or something we haven't thought of yet, it's worth honoring, worth living from, worth building our lives and our world around. Because in the end, we don't have a choice about whether to choose. We have to choose. That's the human condition. And how we understand that condition, how we think about our agency and our freedom, that shapes how we live, how we treat each other, how we structure our society. And those are choices too, choices about meaning and value, choices that can't be made by science alone, but require philosophy and ethics and wisdom. So the question of free will, far from being an abstract puzzle, is one of the most practical and important questions we face. And grappling with it, thinking deeply about it, that's part of exercising the very agency we're trying to understand.